Good morning, everyone. Thanks for waking up early, especially since we're going to talk Windows features. Uh, Credential Guard is one of the biggest changes Microsoft has done to their OS architecture as a whole and lately. And it's interesting on its own, but I think some of its ideas could eventually make their way into Linux and KVM, independent of Windows. So yeah, it's worth looking into it. On top of that, we really want to be able to run it on Windows guests, which is nice on its own. We really want to have some discussion, so I may rush through some of the slides, but that's the point of this anyway. And a quick introduction. I'm Nicholas. Anel here will share the presentation with me. We're kernel and hypervisor engineers at AWS. We build the Nitro hypervisor, which powers most of EC2. It's a set of custom user space components and Linux plus KVM, although we do have 1,000-ish downstream patches. It's a gap we're trying to close, and this is one of the examples. The line of work we do is essentially building a hypervisor that would do all the operations you expect from a cloud provider, so from configure and launching VMs, live migration, live update, but also running more esoteric workloads like GPUs, AI acceleration, overcommitted platforms, and confidential computing like SEV-SMP. All the work we are presenting here isn't strictly ours. The project was started by Evgeny Yakovlev, and it was later joined by other engineers. We're gonna introduce virtualization-based security, which is a Microsoft concept, and go slowly into what VSM really is, and Credential Guard as well. Then discuss the actual guest hypervisor interface, and finally discuss our upstreaming plans. So as we were talking with our colleagues here in the conference, we realized there's some confusion on how we might be running Hyper-V and Windows guests. A lot of people assume that we were doing nested virtualization, where KVM would launch the Hyper-V hypervisor at level 1 and then have a Windows guest as a nested level 2 guest. That's actually not the case. What we're doing is emulate Hyper-V in KVM and running the Windows guest as a level 1 guest. So yeah, it's important to have that clear. So let's talk some naming schemes Windows introduced. First of all, you'll see it all over the documentation, and it's important to see how it's layered. Virtualization-based security is a catch-all term to refer to all the technologies that rely on hypervisor to create isolated virtual environments, as well as harden the operating system. I'll give some concrete examples, but the core concept behind it is benefiting from the fact that would give more trust to the hypervisor than the guest operating system, and especially in the cloud computing world, but as well as the desktop world if you're running Windows. And you can leverage that extra protection boundary to implement features that further protect your operating system or secrets. Device Guard is an example of this. I'll give an overview, not very precise, but it'll give you an idea of what happens. It prevents untrusted code from running in Windows. What would happen is that Windows will ask the hypervisor to remap the whole system memory as non-executable, and only after verifying each one of the binaries in the system, it will ask again the hypervisor to remap those memory ranges as executable. So your attacker that has compromised the operating system won't be able to inject new binaries into your system as long as he hasn't compromised the hypervisor as well and the whole interface, VSM interface. Yeah, Credential Guard follows a similar approach, but it's meant to hide secrets from the kernel and also provides an interface to interact with the secrets in a way that the kernel will never really map them into its own memory. So again, Hyper-V will be asked to remap the memory ranges where these secrets are stored as non-accessible, and yeah, essentially an attacker won't be able to use them. Virtual secure mode, VSM, is what Microsoft defined, is the primitive that Microsoft defined to build these sort of features. And it's the core guest kernel to hypervisor hypercall interface and all the semantics, and it's defined in a spec. We refer to it as TLFS, and Microsoft publishes it. It's a best effort spec. It doesn't go all the way down, so there's some amount of reverse engineering involved when implementing all this, but it gives you a good idea of what you're meant to be doing. Actually, this talk should have been called Enabling Hyper-V Virtual Secure Mode in KVM, but we figured that mentioning Credential Guard would bring in more people in. Let's see. Some platform requirements. I'll be very fast here. Secure boot. This is essential to be able to trust your bootstrap. Otherwise, an attacker can just mess up with your booting setup and disable Credential Guard. A modern CPU, of course, UEFI lock, again, to avoid an attacker from disabling Credential Guard, and TPM. Now, Anel is going to start with an overview of VSM.
Yeah, so hi. Yeah, I'm going to give a quick introduction into VSM, introduce some of its core concepts, and then also give a few details on how we actually implemented it. So VSM, or Virtual Secure Mode, it provides a security boundary using virtual trust levels, or VTLs. VTLs are basically privilege levels. So they are hierarchical. The higher the VTL number, the more privileged it is. Hyper-V spec provides or defines up to 16 VTLs, but in practice, we've only seen VTL 0 and VTL 1 being used. Then VTL 0 would be the normal mode, and VTL 1 is the secure mode. VTLs are orthogonal to ring levels. So when you have two VTLs, you still have your kernel and user modes, but VTL 1 kernel is different from the kernel that runs in normal mode. So it's a small, secure kernel. Yeah, and the basic idea is that even if your kernel in VTL 0 is compromised, you still have another more privileged VTL 1 that can protect secrets or prevent execution of unsigned binaries. So VTL is an attribute of a vCPU. So each vCPU always has one active VTL that it's running in, and then it can switch to a different VTL via either hypercall, or it can be forcibly switched into a different VTL via interrupt or intercepts. So for each CPU and each VTL, there are certain private registers and MSRs, but some registers and MSRs are shared between VTLs of the same vCPU. And finally, for each VTL, there are different memory access permissions. So that's how VTL 1 protects or hides data from VTL 0. And Microsoft implemented this for both x86 and ARM. But yeah, we implemented it for x86. So a similar analogy, an interesting analogy is to ARM Trust Zone. So you could think of VTL 0 as normal world, VTL 1 is the secure world, and then hypervisor would play the role of the secure monitor. How does VSM get enabled? So VSM could be enabled by, for example, setting up Credential Guard in your group policy, and then it will actually get activated on the next boot. So in a normal case, when Windows boots without VSM, you have your bootloader that loads the kernel of the normal mode and then launches the user space processes. But when you have VSM enabled, bootloader would find the UEFI variable that will tell that VSM is enabled. It will then load secure kernel. Secure kernel will go on enable VSM, jump into VTL 1, bootstrap vCPUs, then launch the secure processes, for example, Credential Guard. Then, after it's done executing, secure kernel jumps back to VTL 0, gives control back to the bootloader, and then the normal boot process continues. So yeah, as I mentioned, there are two ways a VTL switch can happen. So the first one is a synchronous one. That one is when guest actually asks to be switched into a different VTL. That happens via hypercalls. So a jump into a higher privileged VTL1 is VTL call, and then going back to a less privileged VTL0 is a VTL return. From the hypervisor perspective, the main thing here is just is to store the content, the private state of current VTL, load the context for the next VTL, and yeah, basically return, give control back to the guest. Yeah, I forgot to mention, so for each VTL, there is a private interrupt subsystem. So yeah, during VTL switch, you would also want to switch into correct APIC. VTL return from the hypervisor perspective is exactly the same. Restore the previous VTL, store the content of the previous VTL, and then jump into the next VTL. Yeah, and the second way the VTL switch can happen is when CPU is forcibly switched into a different VTL. That happens via interrupts. So two rules here. First, all interrupts are now targeting a VTL, and that is basically derived from the origin VTL of the interrupt. So that would be if CPU is running in VTL1, then the interrupt that it's sending is gonna target also VTL1. All external interrupts are targeting VTL0. And the second rule, VTL1 always has precedence over VTL0. So if CPU is running in VTL0 and the interrupt that gets injected is in VTL1, tagged with VTL1, that CPU is switched into VTL1 so that it can go and process that interrupt. When the opposite happens and CPU is running in VTL0, in VTL1 gets an interrupt of VTL0, that interrupt is saved, but it will only get processed when that CPU voluntarily issued a VTL return and went back into VTL0. Yeah, so some implementation details. So what we've done, we basically have extended the vCPU state to have multiple sets of those private registers and MSIs. And we did the same for APIC. So now each vCPU can have multiple APICs, one for each VTL. Yeah, and the main challenge that we've seen with this approach is that it's quite intrusive. It goes into core x86 vCPU code. So it was, and there are a lot of edge cases where you have to adjust for the fact that you have now like multiple APICs and multiple vCPU states. And second thing also for stuff like live migration, serialization and deserialization becomes more complex because you have to restore context for both active VTL at the time and the inactive VTL that CPU was not running in. And finally, my VTL protections, memory protections. So that's how VTL1 would hide data from VTL0 or how it would prevent execution of unsigned binaries. So CPU, depending on which VTL it's running in, would have different access permissions to memory. Otherwise, the GPA to host memory mapping is the same for both, except overlay pages. Yeah, so basically the biggest difference is just memory access permissions. So VTL1 can request hypervisor to revoke, read, write, or execute access. If hypervisor notices that VTL0 is trying to violate that access permission, hypervisor can inject an intercept and notify VTL1 of the violation. Yeah, and implementation. So first thing, what we've done is that we used separate address spaces for each VTL. In that way, you have a different set of memory slots for different VTLs. So that's how we achieved isolation between them. It also allows to do stuff like mapping overlay pages to different host memory for different VTLs. And that's a requirement for VSM. And the second thing, for the actual protection changes, we used memory slot wide access access permissions. So the read-only slots were already supported by KVM, and we've extended it with non-executable and also completely non-readable, non-accessible memory slots, and that allowed us to support the full set of required permissions. So what we would do is that, if you have like a big giant memory region and then there is a page in the middle that needs to be protected, we would remove that slot and replace it with 3 new ones, and then the one that was in the middle, then it gets a new permission. So now it's a protected region. So yeah, we quickly realized after implementing it that there are a few problems with this. So first, you need to either suspend VCP use while you're making this change, because you may get into this inconsistent state while you deleted one slot and then haven't fully replaced it with all the 3 new ones. So you either need to stop all VCP use, or you need to do this whole operation atomically. And that's what we've done. But still, even with this optimization, we saw that it's not very efficient because Windows makes like hundreds and thousands of those changes while booting. Another thing, of course, that you can see here, we're only interested in changing permissions for this small region in the middle. And instead, we're actually operating on this giant GPA range. To achieve a better performance here, we also introduced targeted zapping when doing that atomic slot update. And with this, I'll yield back to you.
So in terms of I/O accesses, there's a big rule. All I/O memory accesses happen in VTL 0. And this brings another set of problems because whenever VTL 1 decides some memory region is accessible to VTL 0, we have to reflect that in the IOMMU. And this happens during runtime and concurrent to other I/O. So IOMMU changes have to happen in a special way. They have to be atomic and always present a valid view of the I/O mappings. We also need to support being able to change the backing memory of an IOVA. And this is because we can't really deal with no access mappings in our hardware, because some of our DMA controllers can, upon getting a PCIe error, can't walk back and don't have the context to realize which virtual function triggered that PCIe error. And if you're running a cloud computing company, not being able to know which of your clients is trying to break DMA, it's a problem. So we're forced to shut down the whole PCI bus, and that's not acceptable. So what we're doing instead is, upon getting a non-access mapping, we redirect that IOVA onto a scratch page, which we know to be safe and won't contain client data. So yeah, it's another requirement to how we have to do IOMMU updates. What we did is introduce a new IOMMU driver callback that we call remap. It, again, atomically updates IOMMU mappings during runtime with all the requirements I mentioned. We implemented this for both Intel and AMD, and funnily enough, it's the only part of VSM that is vendor specific. We also had to implement merging back into huge pages, because VSM has this pattern where it will protect a memory range, do some work, and unprotect it. So that was fragmenting page tables a lot, and this is hurtful in terms of memory consumption, but as well as if you're trying to do live migration, it's not ideal. And yeah, we expose everything through a VFIO IO control, nothing special about that, just going over the VM's IOMMU domains. So what are our plans for upstream? We first of all feel bad that we didn't have an RFC or something before this talk. So we published our work in progress code. It's very rough and insecure, and I wouldn't call that a full Credential Guard VSM implementation, but it's something, and it runs on a fully upstream virtualization stack. No, this is just, oh, is this the implementation we already described or an upstream one? a better one. No, this is the downstream one, but we will be working iteratively and making it better. And I'll describe the work we're planning on doing. So, yeah.
The one that we shipped in EC2 obviously has the security features.
Oh,
lagging here.
My bad.
Just
Yeah.
chiming in.
This is a limited rebase of what we have, and it's a starting point. No, Alex did good here. Thanks. So yeah, we have three main challenges in terms of upstreaming VSM. First of all is finding a better way of managing VTL state. And I think it's pretty clear that the proper way of doing it would be having a struct vCPU per VTL and finding a way to map specific VTLs to the specific guest CPUs. And that can be done easily through the epic ID, the MP state, and the VTL marker we will introduce into the struct vCPU. VTL switching should be almost trivial because it's just switching, running another vCPU, and as well as serialization and deserialization, which comes for free. There's still some share state, and then there's also interrupt injection, which will bring in new code, but it should be way more concise than what we did earlier. Another thing we're planning to introduce is memory protections, and this will go on a second patch series, hopefully. We want to piggyback on the proposed memory attributes IO control that Intel wants to introduce for guest private memory. It pretty much does everything we need, so being able to change the protection on specific GPAs, and it's not bound to memory slots, so it's faster and simpler. The only problem we have with the current implementation is that we don't have a way to map specific memory attributes to specific VTLs. Historically, how we do things, we would add address space support, but maybe that doesn't really fit in the memory attributes abstraction. So it's something we would love to discuss. We could add some way to add extra ancillary data, or I don't know. I'm open to hear ideas. Otherwise, address spaces works for us perfectly. For IOMMU protections, our plan is to rebase that remap callback we introduced in the IOMMU drivers, feed that into IOMMUFD, and send an RFC independent. We have some other workloads that might benefit from this internally, so overcommitted platform and some live migration setups will benefit from having this sort of APIs, but I'm sure people from outside the cloud world can tell me more use cases for IOMMU remap operation. Okay, so that's pretty much it. I hope you have a better picture now of what VSM is, and we'll appreciate any comments, criticism, and suggestions. Thank you.
Hi, I have a question about the big picture. So in the beginning of your presentation, I think you had a slide showing Hyper-V is running. We're not just doing the Hyper-V enlightenments. Can you go back to that slide? So my question about that is basically, how do the concepts that you've introduced map to that diagram? For example, is the VTLs, it sounds like they're implemented in the KVM kernel module. Well, oh, hang on. I got it the wrong way around, right? So you're not doing Hyper-V in KVM.
This is bad. This is good.
Okay, so my next question was, is all of this stuff encapsulated inside the KVM kernel module, or is there stuff that goes out to user space and then the VMM needs to do some of it?
Some parts of it go into QEMU and the VMM, whichever you use, and some parts stay in the kernel. For example, interrupt management will be in the kernel, in KVM, sorry. Some higher level stuff can be handled in QEMU, especially right now, some memory management, memory protections have to go all the way to QEMU to then support stuff like live migration and so on. You need the user space to be aware of all the memory protections that are happening on the system.
Okay, thank you. That's what I was curious about.
couple of questions, not related to the implementation, but more about VTLs in general. So how often do VTL switches happen, and how slower is the right thing, like the right side, so wrong thing?
Nested, you mean?
Yes.
How often would you know, like a good number?
Most of it happens during boot when the whole VSM gets enabled, but then we also see that there are like a few VTL protection changes during runtime as well. And also, when we were doing the memory protections, we also did a few like measurements on like strictly around that. Yeah, most of that happens also during Windows updates. So there are some kind of probably set up for that, secrets that want to be hidden. We haven't measured what would be the difference between using nested versus KVM enlightened Hyper-V, if that was your question.
As the other two mentioned, they joined the team slightly later. We did initially measure the overhead of the Hyper-V solution, and that was roughly, depending on your workload, somewhere between 10 and 15% compared to not doing VSM. Obviously, doing VSM always has an overhead, regardless of what you do. But in normal operation, it's close to free because you do like, I don't know, 10 or so enters to VTL1 during normal operation.
So basically 10%.
Second?
10%.
So Hyper-V gives you a 10% overhead. Yeah, that's the right-hand side.
Yeah, thank you.
I'm not sure if there is a use case for something like nested credential guard, but does your work here potentially enable that if it were to be implemented?
I'm not sure what do you mean by
So imagine you have a credential guard VM that wants to run a VM. I don't know if there's a use case for that, but I mean, it seems like, since it's third level nesting.
Okay. I'm not sure it would even be possible nor secure to begin with. Or maybe no, I don't think that's the idea behind it. What we know can happen is that for some nested setups you have an extra VTL level, which is something we just discovered, and it's not publicly announced. But that's another story. Yeah, so no, you wouldn't be doing that inside the secure world.
Mm-hmm. Thanks.
Thank you. Okay, well, I guess that's all. Thank you very much.